at which field each of the nuclei was getting into resonance. And you're actually plotting the x scale in the form of a magnetic field axis. Now let's do that. We'll keep filling the same spectrum and the numbers somewhere. Okay. Let's say this fellow gets into resonance at some field. And what is that field going to be? It's not going to be 2.3487 because 2.3487 is actually the magnetic field required for a bare proton. This is not going to be at that. It's going to be at some value, but rather close to that. Or at some value, not rather close to that. Some value of the field, I'm going to get this guy getting into resonance. Then what do? I keep changing the field. And when I keep changing the field, this fellow will get into resonance at some other field. And let us say, I just call this field as 0, that's my starting point. And then let's say that at 3.26 microtesla away, this guy gets into resonance. In fact, these are the more realistic numbers. So at some field, magnetic field, this fellow was into resonance. I now change the field. And when I change the field, this is what? Shielded or less shielded. This is the most shielded. So what should happen over here? Well, I need less field, right, to get this guy. So when I change the field, I decrease the field. And I decrease the field by, let us say, about 3.26 microtesla. Very small change. This fellow is into resonance now. And therefore I get a spectrum out here. Let's not worry about these two because it's enough to have this one peak for our discussion. So it is 3.26 microtesla away, I'm going to see this shift. What is 3.26 microtesla in terms of frequency? Very easy to calculate because 100 megahertz is what field? 2.348 Tesla is 100 megahertz. We know that. Therefore, 3.26 microtesla will actually correspond to, if you work it out, 139, let me make it 140 hertz. So, which means that if this fellow is absorbing at some frequency, let us say 100 hertz or something, where is this guy absorbing? This guy is absorbing at a frequency that is 140 hertz less than 100 megahertz. That's why I kept saying the last time when I said this is something 100 megahertz, this is 99, this is 98, as if to tell you that the shift is 1 megahertz. No, the shift is not 1 megahertz. The shift is in the form of a few hundred hertz. So which means if TMS is absorbing at a certain frequency, where is the metal proton of alcohol going to absorb? It is going to absorb at a frequency which is 140 hertz less than where the TMS absorbs. Because the field that is required to get this into resonance is only like 3.26 microtesla away. So this is the difference in the field that is required to get this guy into resonance versus this guy into resonance. That's the difference in field I require. But this difference in field actually translates to a frequency difference of 140 hertz. What is the fundamental frequency of the machine? 100 megahertz. But these peaks are separated by about 140 hertz. That's it. So now, how do I express this? I can express it in one of two ways. I can take 3.26 microtesla and divide it by 2.348 Tesla. I am normalizing. And what is this number going to be? It's going to be 1.39 into 10 power minus 6. That's what you will get. Alternatively, what can I do? I can take this, or maybe this is 1.40 to 10 power minus 6. Alternatively, what can I do? What is the frequency difference there? 140 hertz. and I divide it by the operating frequency of the machine. And what is the operating frequency of the machine? And what is this number equal to? Right? So, whether I take the magnetic field difference between these two and divide by the operating magnetic field of the machine, or I take the corresponding frequency difference, which I can very easily translate, because I know 3.26 microtesla must actually correspond to 140 hertz. Well, I know 2.34 Tesla corresponds to 100 hertz. So this frequency difference is 140 hertz, and if I normalize at 140 hertz with the operating frequency of the machine, which is 100 megahertz, then what do I get? 1.40 to 10 power minus 6. Generally what you do is, you forget this part and you say it is 1.4 ppm. Actually it is 1.4 here. 1.40, 1.40, 10 power minus 6. So I don't give the 10 power minus 6 part. It is 1.40 into 10 power minus 6. It is the same thing as saying 1.40 parts per billion. Therefore, my x scale now is simply going to be a number that is a normalization of the frequency difference divided by the operating frequency of the machine, or a difference of the field divided by the operating frequency of the field. Both are absolutely identical. So if this difference is 140 hertz, then it simply means in terms of ppm, it is 1.4 ppm. What will be the shift if I use a 200 megahertz machine? I'll get 240. And therefore, if I divide that by 200 megahertz, I will simply get again 1.40. So as long as I take the frequency difference between two peaks and I divide by the operating frequency of the machine, I am going to get one single unique number for a given type of proton in a molecule, and independent of which machine it is, I am doing the experiment. That's the whole idea. So now therefore, if you look at the x scale is going to be simply a number which is this Lamarck precession frequency minus this Lamarck precession frequency divided by the operating frequency of the machine. That is my x scale. And that x scale is actually called the delta scale and is expressed as ppm. So where does the TMS occur on the scale? 0 ppm. That's a reference. Where does the metal proton occur on the scale? Roughly around 0.91 ppm. Where does the hydroxyl occur on the scale? Around 4 ppm. So anytime you see a peak near about 4 ppm or thereabout, you know I am dealing with a hydroxyl proton. Anytime I see a peak somewhere near 1 ppm, I know I am dealing with a metal proton, because the metal proton should come at 1 ppm, meaning it should come at 140 megahertz or around 100 megahertz for 100 hertz for a 100 megahertz machine, 200 hertz for a 200 megahertz machine, 400 hertz for a 400 megahertz machine, but if you normalize it, it's always going to be 1 ppm. And therefore, the x scale over here is just going to be a ppm scale, and it's given delta, and this delta is actually called the chemical shift. And what do I mean by a chemical shift? It's the shift relative to my tetramethyl silane, and expressed in units of frequency but divided by the frequency of the machine itself, and therefore just a number. And since I have this 10 power minus 6 that comes in, because of the fact the machine is actually a megahertz machine and the frequency shift is always going to be in hertz, you simply throw that minus 6 away, 10 power minus 6 away, and use the terminology of parts per million. So therefore, the whole scale will be divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in terms of ppm, with a big peak at 0 ppm, which is always going to be your tetramethylsilane, and every other group in the molecule which has got protons on it will give me peaks out here. So if I look at, let us say, the methanol molecule, what do you think will happen? Somewhere over here, and 1, 2, 3, 4, somewhere over here. And in what ratio? 3:1. The fact I get something near 1 ppm, I know it's metal. The fact I get something near 4 ppm or thereabout, I know it is a hydroxyl. And therefore, you get the same sort of powerful analysis that he did with IR, where he could just look at the frequency of absorption and tell what group it is. Here again, I look at the resonance frequency in NMR and I'm able to tell you what it is. Except this is more powerful because I can also tell you how many hydrogens are there. IR can't tell me that. IR you simply say there's a CH2 group. How many CH2 groups, I don't know. Whereas here, I'm able to tell you that. Because the area under the peak over here is actually a measure of the number of hydrogen atoms present in that particular group. But if I did ethanol, what would happen? I will have one here, and one here. But then, the fact that one of them shows at 1 ppm, another one shows somewhere near 2, and the third one shows somewhere near 4, I know that I'm dealing with metal, methylene, and hydroxide. Benzene will show up somewhere else, and we will see where that is as we go along. But the point is, the scale is actually a normalized scale. So that irrespective of what frequency you used, 400, 600, 800, 1000, 200, it doesn't matter. Methyl proton will always come at 1 ppm. But what is 1 ppm in terms of frequency? Let's get that straight. If I say 1 ppm, what is it in terms of frequency? Well, I don't tell you what machine it is, right? If it's a 100 megahertz machine, how much is 1 ppm? 100 hertz. If it's a 400 megahertz machine, what is 1 ppm? 400 hertz. So 1 ppm will actually be 100 hertz, not 100 megahertz, 100 hertz for a 100 megahertz machine. 1 ppm is actually 400. That scale actually means 400 hertz if I'm dealing with a 400 megahertz machine. So which means that if I show a tick mark here and say it is 1 ppm, and if I ask you what is the frequency difference between the Lamarck session frequency of this peak and this peak, the first thing you got to ask me is what's the machine operating frequency. If it's a 400 megahertz machine, then this difference is going to be 400 hertz. If it's 100 megahertz, it's 100 hertz and so on. But in terms of ppm, they will always show up at the same place because I have done this little normalizing. And that makes the data from different machines to be absolutely comparable. Otherwise, you won't have a problem. Each one will say, no, it is shifted by 400, shifted by 200, shifted by 100, and so on. And to eliminate this sort of an ambiguity, we said, let's normalize the whole stuff. And when you normalize, you get a number that is independent of the machine frequency. And that's something that's very important to realize, that 1 ppm is 1 ppm for a given group, irrespective of what machine we really use. Is that clear? Or if there's any ambiguity, we need to get this sorted out before we go any further. Now let's get into another concept that is going to also lend a greater power to this whole analysis. But before I do that, let me make some few announcements. As I said, I'm going to be away for this week. Really sorry, it was something I accepted a long time ago without realizing that it was getting close to the exam. But anyway, I think we will still make it. The Wednesday class and the Friday class, I asked my colleague Sukumar to come and solve problems for you. He will not take any class, but I have given an assignment. So he will solve problems for you and he will show you NMR spectra and teach you how to interpret NMR spectra based on what we have learned now. So I want to get to a point today which is going to be enough for you to start interpreting NMR spectra. And what Sukumar will do is actually present you a few spectra and help you go through the whole process of how you use the technique that we have learned now and interpret spectra and tell what the compound is. So that's very, very important because I'm certainly going to give you a bunch of spectra in the exam and ask you, tell me what the compound is. Simple spectra, not very complicated ones, simple ones. But you need to have some practice. So you will do that for you. I come back on Saturday and Sunday we meet and then we take this forward. But if you have any questions whatsoever on the assignments or whatever, you're always free to get back to me and discuss that with me. Even during this week, if you need to call me, just call me, and because I'm just going to be traveling, so I will be able to answer your question. So, but anyway, Sukumar will be here on Wednesday and Friday, working on these problems and showing you spectra and helping you interpret spectra, so that we get forward this whole process. So that on Sunday when I get back, we will just do what's left and then we go on to PSR. Okay, now let's look at one more thing. So now we know one thing now. We know what the NMR spectrum will look like. It's going to be at this thing, horizontal axis, and the horizontal axis is delta, it's in ppm, and there's one big sharp peak, always at 0 ppm, and that's going to be your tetramethylserine, which is a reference. And how do you record this reference? The moment you give your compound the NMR spectroscopist will always add a small amount of tetramethylserine to your compound, put the sample into your machine, and record it. The machine will record the spectra due to your samples and due to TMS, and you put all of them together, and then you make your assignments. And we saw how this works. So let's say if I have how many peaks must I get for this NMR? 1, they're all equal. How many peaks can I get for this one? Oh, I must get 2 now, because this chlorine has completely messed up with the symmetry of the molecule, and therefore I'm going to get 2 peaks, they're non-equivalent. And which is going to be closer to TMS and which is going to be further away from TMS. The metal will be closer to TMS and roughly around 1 ppm away, and the other flow will be closer away. And in what ratio of the areas? 3:2, because there are 3 and 2. So this ratio will be 3, this ratio will be 2. That's what it is.